Good afternoon, guys. In this video, we'll be talking about electric current and electron drift. So quickly, what is electric current? Electric current is the rate of flow of charges of the same sign across a conductor. Now I want you to know that when we talk about electric current, what is responsible for the generation of electric current is as a result of the voltage produced from a source like a battery, or you have a cell whatsoever. It produces a voltage. This voltage then drives charges across a conductor, and that is what is responsible for the electric current generated. So now let's assume that this is a conductor. If this is a conductor, the conductor is made up of a particular material, such as it can be aluminium, it can be copper, or whatsoever. But I want you to know that these materials are usually metals. So metals usually have charges like electron in their outermost shell, and these charges are found mobile in their structure. So when I'm talking about copper atom, a copper atom is having in it electrons of copper, which are what? Fully mobile. Now these copper electrons is what is responsible for the generation of electric current across a copper conductor or a copper material. Now if we have the electrons to be here, these are the electrons. What I want you to note here is that when this copper now is connected to a cell, if this copper is connected to a cell and the cell is put on, then the current, the voltage that which this cell generates will drive this current towards opposite direction. And when it drives the current in opposite direction with a velocity, it drives the electrons with a velocity, or drives the charge with a velocity called the electron drift, velocity. So it is usually a small velocity that moves the material, very small. As I said earlier, that what is current, and I will regard current as what? As the rate of flow of charges, the rate, that's the change in the charges per unit change in time interval for the charge to flow. So here, what you have is that this charge that you have here is the amount of charge that you can find in a metallic material. As we said, this is a metallic material now. The sum total of all the electrons that you have across this particular conductor or material is this Q. Now, you always have these particular electrons to be the charge carriers. Now, for conductors, we usually have what referred to as charge carriers. And charge carriers are usually protons, electrons, but in semiconductors, we usually have something like holes, and we always have free electrons too. So here we can have it to be the number of these charge carriers times the charge carrier we are dealing with, which can either be a proton or an electron. But for this conductor now, it will be an electron. Let's just put E. Now, if you put E here as the electrode, the charge of electrode, which you must note, as discovered by J.J. Thomson, is said to be 1.602 times 10 raised to the power minus 19 coulomb. This is the value of charge of electron. Why this N that you have here is the amount of charge per unit carrier. So this N is equal to your amount of charge that you have per unit the carrier. Now, what we want to bring about here, what we want to discover here is that it's for us to know that in a nutshell, when you're talking about charge is said to be what? Your current times what? Times the time. And at the same time, we see that our current is equal to what? The charge per unit time. We want to go about the derivation of the electron drift velocity now. How do we derive the electron drift velocity? let's see. In case whereby you have the length of this material and we have the velocity, normal is a linear velocity. And what do we call this linear velocity? A linear velocity will be distance over what? Time. But because the distance across the material will always be the length of the material, then we change it from d, you can change it to the length of the material. When you have it as the length of the material, we have that your v now is equal to the length. And how do you calculate length? We have that our length, how do you calculate the length? Length is equal to what? That is volume over what? Area. Our length is equal to volume over area. Also, we have that our density, when we talk about density, to calculate the concentration, that is the total amount of charges that you have in a material, we always consider the density to be the concentration of the charges that you have in it, which is said to be what? The density is equal to mass over the volume. In a nutshell, I can say volume is equal to what? Is equal to mass over density. This is our volume. Now, when you come back to this place where you have your mass to be m, we have our density to be d. Now, when you come back to this expression, I'll say my length is equal to volume. What's my volume? Mass over density all over what? Area. And this is equivalent to mass over what? AD, which is our density. This is for the length. And when we want to get the velocity, our velocity will be said to be what? What's our velocity? Velocity is said to be the length over the area. And what do you have as length? The length is mass over area times the density. Then we have divided by what? Time. We are dividing by time. But if we are dividing by time, we can change this to multiplication sign and to be what? Times 1 over what? T. That is when we change it to multiplication sign. It becomes 1 over t. Now, this is our velocity. If this is our velocity, we want to relate this velocity with our what? We want to relate it with our current. So we have that our current now becomes what? What's our current? Our current will become what? Charge over time. Now, how do we get time from this expression? Time is said to be, that is mass over, that is what? VAD. When you cross multiply, we have to be VAD. Where V is our velocity, A is our area, cross-sectional area. That's the cross-sectional area across this place. So we call it the cross-sectional area. Cross-sectional area. And we have our D to be the what? D is said to be our what? The D is said to be our density. So from this expression, when we put in your T here, what's our T now? Our T becomes times the same thing. This one goes up and the other one comes down. We have to be VAD and we have to be over M. And don't forget, what's our M? Our M is said to be the mass. That's the mass of the. We have to be the mass. Now let's see. From this expression, I want you to get this clearly now. From this expression, we can see that our Q, which is said to be the Q is said to be the charge. And what is our charge? Your charge is what? Is the number of electron, the number of charge carrier times what? Electron. But do not forget that your mole, the formula for mole shows that your mole will be mass in gram over the molar mass, and your mole is as well stated to be, what's your mole again? For subatomic particles, your mole is said to be number of atom over what? Over 6.02 times 10 to the power 23. This is called the Avogadro's number of atom, and this Na is the number of atom that we're talking about. Now see, from this expression, I have that my mass, if I should cross multiply, what will be my mass? My mass is said to be, that is number of atom times the molar mass. Let me just put mm over, what do I have here? I have 6.02 times 10 to the power what? Times 10 to the power 23. Now, to bring in this particular expression here, instead of me writing mass, I'll put the expression here. Then I have that my current is said to be what? Is said to be Q times VAD times this M. What do you have as M? You know, this is division, so it means that what you have down will go up and what you have up will come down. Then to give you 6.02 times 10 to the power 23 divided by what you have, NA times NN. Now, do not forget that what you have here is Q. And what do you refer as Q? Q is said to be what? NE. That is the number of the charge carrier times the what? The number of electron. So I will say that my I is equal to number of the charge carrier times electron times what you have here, V, you have your A, you have your D. And what do you have here? You have your 6.02 times 10 to the power 23, all divided by what do you have here? Your Na times Nm. And what do you call Na? You said Na is said to be what? That is the number of atoms. Now, when you look at this expression fully, we can easily say that the current is said to be what? I'll give a very short cut to remember this formula. Just write EVAN, let me just put S here, over what do you have? You have your MM. Now, how do I get this? I get it by saying that here, this will cancel this. And what do you have left? You have your what? You have your E, this is your E, V, this is your V, velocity. A is your, that is your, what do you have as our A? Our A is said to be the what? Area. What do you have here? NS. This NS now represents the Avogadro's number of atoms, and you just put D. Now, this particular formula is what is always used. You use this formula in all cases to calculate what? To calculate for the drift velocity, in which you have this V here to be drift velocity. So you can as well remember this formula by saying that your current is equal to Evans dad over my mommy. This is I equals Evans dad. This D represents dad. E is the electric charge. That's electric charge of electron. You have V to be your drift velocity. A is your area. Ns is your number of atom. And D, don't forget your Avogadro's number of atom is always what? 6.02 times 10 to the power 23. Your D is your density, and you have it to be what? Over Nm. So I give you this particular mnemonics that your Evans dad over my mommy. Evans dad over my mommy. Where my mommy is your molar mass, E is your electric charge, V is your velocity, A is your area, N, this N subscript S is your what? Avogadro's number of atoms. Then you have to be your I. So I equals what? Evans dad over my mommy. This formula is always used in most cases to look or to calculate the drift velocity. But there is a state in which getting the drift velocity using this formula might not be possible. And what is that case? The case is when you are not given this particular D. It's said to be what? Your density. When your density is not given, what you use to calculate your current will change to I. I'll just give you the formula without no derivation. Your I is said to be I equals what? Even over lambda. Now, what is E? As said before, E is said to be what? What's E here? E is said to be our electron. That's charge of electron. What is V? But this V is VE. That is V subscript E. And what is V subscript E? V subscript E is our velocity. That's drift velocity. So it still remains our drift velocity. Don't mix it up. Your V here is ordinarily drift velocity. But here, to make this formula more easier to use, we make it VE. VE is your drift velocity. Your N here is the number of atoms of that particular material with which the conductor is made of. Now, the number of atoms here is not the same thing as Avogadro's number of atoms, as we stated NS. NS here is your Avogadro's number of atoms. But this N you have here is the number of atoms. The number of atoms of the material you are using. And this L you have here remains the length of the material. That's the length of the material that you are using. In this particular video now, we have about 4 questions. We're going to solve those 4 questions using these 2 formula in their respective case. Don't forget, we always use this formula whenever our density is given. But once your density is not given, you change your formula to even over what? Log x, where your L is your length. And what do you call this one? Evans dad. Evans dad over my money. Okay.